When you see this number, what does that actually mean? Let's look at that. So when I have 5, well, when I know that it's 5, but 5 what? Each of these is 1. So when I have 5, I actually have 5 things. I'm counting something. 5 is a count of ones. I'm going to write that like this. 5 is 5 ones. We're counting ones and we have 5 of them. This underlying idea of multiplication of number, that number is inherently multiplicative, is really powerful and powerful for conceptualizing number and moving into making transferable connections across number forms. That is really powerful for conceptualizing mathematics. When I see 5, I have 5 ones. This allows me to then think about this expression differently. I'm going to read this. This says I have 5 and 3. In this first term, what are we counting? In the first term, well, we're counting ones, and we have 5 of them. In the second term, what are we counting? We're counting ones also. We had 5 and 3. We have 5 ones, and we have 3 ones. We have these 2 terms. These 2 terms are like terms. They're like terms because they're both counting ones. They're both counting the same thing. I have ones and more ones. Together we have 8 ones. So when I look at an expression like this, I can read that. I have 6 2's in the first term, and I have 4 2's in the second term. We have 2 terms. They're both like terms. They're like terms because they're both counting 2's. Let's take a look at that. I have counts of 2's. Here I have 1 2. Here I have 2 2's. We're counting 2's, and we have 6 of them. We need 6 2's. We have 6 2's, and we have 4 2's. Since we have like terms, we can combine them. How many 2's do we have altogether? We have 10 2's. So in this expression, we have 6 2's and 4 2's. Together, that's 10 2's. Now, we have 10 2's, and we can continue to count 2's, but we can count something different. If I have 10 2's, well, what else could we count? Now, you might choose to count ones from here, or perhaps you see that we could also count 10's. Here we have a 10, and here we have another 10. So to have 10 2's is to also have 2 10's. Now, I can keep it as a count of 10's, but we also could change that as a count of ones. How many ones do we have? If I have 2 10's, counting 10's as 10 is your friend, it makes it much more easy. So I have 2 10's or 20 ones. So this expression is equal to all of these things. I can change the count. When we have like terms, we can combine. And when we're counting things, we can change that count. How many terms do we have? We have these 2 terms. In the first term, we're counting 7's, but in the second term, we're counting 3's. They're not like terms. These are unlike terms. They're not counting the same thing yet. So if I want to instead count something different, what could we do? Well, here's a count of 7's, here's a count of 3's, but we know as mathematicians, we can change that count. If I have 7 3's, 1 3, 2 3's, 3 3's, 4 3's, 5 3's, 6 3's, 7 3's, I could instead count 7's. I have 7's, and how many 7's do I have? 1 7, 2 7's, 3 7's. I could count 7's instead. And I still have my 4 7's. Now do we have like terms? So we have 7 7's. So I have 4 7's and 3 7's, which gives us 7 7's. And now from here, I could leave it as a count of 7's. So this then connects to an expression that looks like this. In this expression, how many terms do we have? We have 1 term, and we have a second term. And what's being counted in those terms? Well, in the first term, we're counting fifths, and we have 3 of them. And in the second term, we're counting fifths, and in this case, we have 7 of them. Are these like terms? Well, they're both counting fifths, which means we can combine. If I have 3 fifths and 7 fifths together, I have 10 fifths. I have 10 of these 1/5. I have 10 1/5. Now, I could have that written like this, which you might know as an improper fraction, but I'm going to make sure that it's very clear what we're counting. What we're counting is fifths, and we have 10 of them. I have 10 of these fifths. Now, I need to understand, well, what is a fifth? What do I know about fifths? Well, 5/5 is equivalent to 1 whole. We know 5/5 is equal to a whole because a whole has been split into 5 equal parts. And each of these jumps is a jump of a fifth. 1/5, 2/5, 3/5, 4/5, 5/5. To get a fifth, I've taken a whole and split it into 5 equal parts. Therefore, 5/5 is equal to 1. So then 10/5 must be equal to 2. We've doubled the amount of fifths, so we've doubled the amount of wholes. So if I have 10/5, then we have 2 wholes. We changed our count. We had a count of fifths, but now we're counting wholes. We had like terms, which allowed us to combine, and then we could change the count. How many terms do we have? Well, I have one term, 7 A's, and second term, 4 B's, and in the third term, 3 A's. I have 3 terms. In the first term, I'm counting A's. I've written it like this. I could have written it like this. It means the same thing here. Conventionally, when I have a variable, when I have something like A's, I don't have to include that multiplication symbol. It's already there. I have 7 A's and I have 4 B's. So I'm counting B's and I have 4 of them. And in this third term, I'm also counting A's and I have 3 of them. So we have these unlike terms. Well, some of them are unlike, the A's and B's, but do we have any like terms? Well, yeah, we have some counts of A's. The A's are counting the same thing, so we can combine. I have 7 A's and 3 A's. We have this many A's, and we have 4 B's. We have some A's, we have some B's. We can combine these because they're counting the same thing. I have 10 A's, and I have 4 B's. These are unlike terms. They're not counting the same thing, and I can go no further. So the concept of addition does not change. We understand that addition is combining like terms. When we're counting the same thing, we can combine. So what are you counting?